Okay, so this session we are going to talk about flow flow on circles in one-dimensional systems, and after that bifurcations in two-dimensional systems, and then the rest of the time you can ask your questions regarding the final projects and stuff. Okay, so let's start with flows on the circle. So again, I refer back to Hunaid question. He asked about some important features about the angle, and I can tell you that sometimes it's smart to be like 25 centuries ago's people, like philosophers or mathematicians that introduced something named angle. Why? Because it can bring you the idea of line, circle instead of a line. So we always had this formulation here, like x dot equal to f of x. And then if we want to change this line representation to a circle representation, we just change it to theta dot equal to f of theta. We just call this theta like the angle. And instead of having a flow on a line like this, then we have a flow on a circle. This theta dot equal to a function of theta, it corresponds to vector field on circle, which provides, yeah. You don't have my screen. You don't have my screen. Sorry. I forgot to do this. So probably now you have, right? Okay. I say it again. So we have x dot equal to f of x here, like a line, and we are going to talk about a circle, and instead of this x we replace it with something like theta dot equal to f of theta. And then instead of having a flow on a line like this, then we have a flow on a circle like this. And this corresponds to vector field on a circle, which provides the most basic models that can oscillate, which all we care about in these dynamical systems and stuff. It's applications on spiking neurons and the behavior of the system is about this oscillatory behavior. Why? Because this circle has this property that can eventually return to its starting point. Any point can return to its starting point. Therefore, you have a periodic motion, you have a periodic solution, which is possible to bring you the idea of oscillation. As an example, you can see that here theta dot equal to sine of theta. For finding its fixed points, we have theta dot equal to 0 because it is fixed. Always we put this equal to 0 to find the fixed points. And there are two solutions for this. Theta star equal to 0 and pi. Then sine of 0 or pi will be equal to 0. Therefore, they are our fixed points. Like this, here, and here. These points are fixed points. However, about the stability, when we want to, when we say that, for instance, here for instance, theta is equal to pi over 2. Therefore here sine of pi over 2 is some number like 1, which is bigger than 0. Therefore, it is the representation of instability because it is positive, it is not negative. Therefore, this flow is counterclockwise. And here it is clockwise. Why? Because both of them should attract to this stable fixed point and repelling from this unstable fixed point. So this was just an example. So now let's say we want to have a uniform oscillation. A uniform oscillation. Before that, we can say that we use phase a lot, right? So for phase, we say a point on a circle. It is called a phase or an angle, both of them. So this theta, if I take it like to something equals to something like omega, which is constant, then my theta will changes uniformly because it is constant. Nothing is changing. Therefore, the change in theta is constant. Therefore, it is uniformly changing. One of the solutions for this is d theta over dt, right? Therefore, I can bring this dt to this part and taking the antiderivative, and it's going to be theta equal to omega t plus an initial condition like theta naught. We call this omega like our angular frequency, the frequency on this circle. So, is this solution periodic? So, if we have this circle, then it is eventually returned back to its starting point. And if we have, for instance, if we have this equation here for theta, then every, like, with period of 2 pi over omega, we have the same value for theta. Therefore, it is periodic. And after this time, which we call it the periodic time, it returns back to its initial state or starting point. Therefore, it is periodic. And periodic motions are important because we talk about oscillation. How about non-uniform oscillation? Non-uniform oscillation means that the change in theta, which is theta dot, it is not constant. So here you can see that this f of theta, it is a function of theta, and by changing the theta dot is changing, and by theta dot changing, again the theta is changing, and it is not uniform. So in biology, you can say that we have oscillations in neurons, or we have, for instance, firefly flashings. Let me actually show you a video like this, for instance. We can watch this. That in nature, actually, the fireflies are kind of synchronized with each other, and why is it happening? So they have these fireflies. They have a frequency in flashing, and they are going after sometimes they are going to be synchronized and firing together, and this is why you can see kind of, as one of my friends said, a Christmas tree, and this is actually the idea of coherently responding to the frequency together. They are going to be synchronized, and these things exist in nature always. So Okay, so if I also want to wait, please. Okay, so if I also want to say that, for instance, a work has been done by Professor Pieper and Clemens Kronhofer, and they worked on the synchronous the synchronization on in neural network, uh, like in this grid. All of them are spiking with the Izhikevich model, for instance, and you see that they are going to be synchronized. And for instance, my work is based on this one, and you see that this synchronization also exists in neurons as well. When they are firing, they are getting, like, the frequency are going to be closer and closer. They are in phase, and therefore they are synchronized. Okay, so if we this is the idea that why phase, like the angle, is so much important, because you can have the periodic motion, you can have oscillation. So if we just want to draw, like, sketch this, then we just say, okay, if theta is equal to 0, therefore theta dot is equal to just this part omega, and this is 0. And if theta is equal to pi over 2, then it is 1, and therefore it is omega minus 1, and so on. And with the derivative of it, like in theta equal to 0, then you will see my slope which is negative here, and a slope which is 0 here, and a slope which is 0 here, and you can actually sketch this, right? Theta dot with respect to theta. So you have this ununiformly oscillation. You can see that this theta dot, it's changing, depends on theta, the value of theta. And all of them, like the behavior of it, because it is important about the sign of A and about the value of A, which is here. If it is equal to 0, then you do not have anything. It is just theta dot equal to omega, like the last one, which is uniform. Therefore, this theta as a parameter introduces this non-uniformity, right? So this is how actually parameters play roles. And if you want to bring this idea about this with different values of a's, you can have different behaviors of theta dot with respect to theta. If it is minus something, like the one that we sketched, it is like this, and there is a kind of bottleneck here, which the flow here, it is very, 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 it's kind of like ghost, and it is very slow. And this is why you can see here that on this circle, which is the representation of this theta, the phase portrait of that theta, here it is slow and here it is fast, which we are going to talk about it now. And by changing that A equal to omega at theta equal to pi over 2, you see that it is like this theta axis is the tangent of this graph. Therefore, it is a half a stable fixed point, which here it is positive. Therefore, this part is stable, and this part is unstable, so partially stable. And if it is bigger than omega, then you will see that you have two fixed points. And with these two fixed points in the phase portrait of theta, you have these two fixed points. One of them is stable, the other one is unstable, and between them you have this flow from unstable one to stable one, and from this unstable one in counterclockwise to this stable one. And with this idea of ununiformly oscillations, we are going to talk about those bifurcations. So because here it is just one dimensional, we just have theta, we do not have, for instance, something like r, like the amplitude. We do not have any kind of variable like that, we just have the phase variable, which is theta. Then you can actually say that the amplitude is constant, or we do not care about it. But this is because why it is in one-dimensional system. If we go to two-dimensional systems, then it is different. So now we go and talk about bifurcation in 2D. If you have any question, I am available. Okay, good. Everyone is happy. Bifurcation in 2D. Stable equilibrium, which we have, like our fixed points, or our closed orbits, like our limit cycles, which we talked about. When we change that parameter, for instance, here we had a, or like in mathematically, like in a very general sense. But if we for instance talk about it in neural spiking models, then it can be, for instance, the current, right? So when we vary the parameter, then this stable equilibrium or closed orbit, it is vanishing or changing its stability. If you remember, in 1D system, we talked about the bifurcations. We had the three main parts, like saddle node and transcritical and pitchfork, which in saddle node, for instance, the fixed point were vanishes or generated or creation or destruction of the fixed points, and in the rest it was like changing in stability. So now we have 2D systems. In 2D system, it's kind of pretty much same as the 1D system. In the 1D system, we talked about those values, but in two-dimensional systems, we talked about Jacobian matrix and the eigenvalues, which in p-plane, for instance, in the phase plane, the software, the way that you can draw those eigenvectors and eigenvalues, it is coming from those Jacobian matrices. And if it is equal to 0, the eigenvalue, then you have those three types that we talked about, pretty much the same. If it is a complex number, then we call it like Hopf bifurcation, which is the name of the mathematician. And you can see that, for instance, here, if this lambda 1 and lambda 2, here this lambda 1 and lambda 2, it is less than 0 in the portrait of lambda, like this imaginary axis and this real axis. Then you have two kinds of lambdas, lambda 1 and lambda 2, and as long as they are on this side, then everything is boring. But when they crosses, when these eigenvalues lambda 1 and lambda 2, when they crosses this axis and they cross into this real part of lambdas, exactly at lambda equal to 0, then you see this bifurcation. So bifurcation occurs when eigenvalues cross into real parts of lambdas. And same in the imaginary part. So in the imaginary conjugates, like this lambda and lambda tilde. So this is the basic idea, and now we talk about it in details. This is the bifurcation of fixed points. We also have the bifurcation of closed orbits, which like limit cycles. Limit cycles also can vanish or can change their stability by changing the parameter. This is pretty much same, but geometrically and topologically they are different. So the first one is saddle node bifurcation of the cycle. So we have like a limit cycle like this. We do not have any change in frequency. It means that everywhere it is the speed or the velocity of the change in theta, it is same, it is constant. So there is no change in the frequency. And if, for instance, this one is the stable limit cycle, and this one is the unstable limit cycle inside that stable limit cycle, then by changing that parameter, you see that they are getting closer and closer until they emerge and disappear. A very good way to die, like changing all of the physical laws. And the second one is the saddle node on invariant cycle. The saddle node on invariant cycle, if we want to imagine them or visualize them, we say that it is exactly like it is pretty much like this saddle node one here, this stable limit cycle here and here. However, the frequency is different. Here the velocity, the change in theta dot is kind of constant, but here the velocity is different, and here it is slow in this point that the new fixed point is going to be generated. Like there's a ghost here, and it is here it is very slow, like very close to that bottleneck that we talked about, and here it is fast. So this is the difference between the velocities of or the change in the theta. So here this but as you can see that here, for instance, in saddle node, the limit cycle is going to be destroyed, but here it is invariant. The limit cycle exists until the end. However, by changing the parameter, this stable closed orbit, at the bifurcation point, a new half a stable point are generated here, and so this is the bifurcation point. It means like that parameter like a is equal to 0, and when it is positive, when you increase that parameter, then two fixed points are created here. Like one of them is unstable, the other one is stable. However, because it is in 2D, then it makes sense that here, for instance, here this one is saddle. This one is saddle because from these sides the trajectories, like the flow, are repelling from them, but from these sides the flow are toward this saddle node. So this is why we call it saddle. In 1D it doesn't make sense that much, but in 2D it pretty much makes sense. And by this creation of this saddle and node on this invariant cycle, this periodic orbit which we had here, it is going to be destroyed. So let me see if you have a question. No. Okay. So if you remember, we talked about and please open your face plane, the software, because we want to visualize them. You see, these kinds of things are important because uh, out of these works and equations and the different qualitative functionality or the structure of the system, you can you can you can write kind of a story, like a scientific story. Like we have a great guy named Daniel Kahneman, and he has a book like Thinking Fast and Slow. It's pretty much like this invariant cycle. So I don't know than that. So it's so the system one type of thinking is very fast because it is based on emotions. For instance, if you see a portrait of an angry man, then you simultaneously get the whole idea out of this portrait. However, if I tell you that what is the answer to 17 times 24, then you need some time to compute that. You need to analyze it, and this is where system 2 type of thinking playing role. And the interaction between system 1, which is very fast, and system 2, which is very slow and needs these analyzes, the interaction between them brings you the story that you can connect them. It actually brings your your belief system about the whole world, about evolution, about where you live, what kind of a story that you have. All of these things is coming from those stories. And even the whole history of science is based on a creation of a story. So the way that I am saying that you should write a story is in this sense, not a very like naive way. So so for understanding this, let's go back into this. So if for this saddle node of fixed point, for instance, we had this, right? So the main point in this example that, for instance, we had previously is that in x dot, or you can talk about it, for instance, here r dot or theta dot, is this square root, this square of x. So it is x squared. However, in transcritical, for instance, what did I do? Both of them are squared, but here you do not have this x, but here you have this x. But here in supercritical and subcritical, you have these cubic terms, which one of them is positive, the other one is negative. By different choices of your value, like this a, this a, this a, this a, and all of them are same, we do not care about this y dot, right? Because y dot is just very boring. There is no coupling, there is no nonlinearity, and it just says that you have a damping in y-axis. That's it. So you can take other examples, but here the interesting part is about this x dot, which it has these nonlinear terms. So with different choices of this parameter like a, you have you can bring these analyzes in your phase plane and make those kinds of stories, which actually in general the way that you can arrange these facts and connect these facts, it leads to a publication, right? So you if you do this now, I want you to check these things and let's see these behaviors, like x dot equal to a minus x2. A minus x2. And y dot equal to minus y. So if I have, for instance, here, if I have something like minus 10 and I don't have any y, or if I have something like minus 1, then you see that we don't have I don't know why I always do this mistake. So you have this null line again, the change in y prime, and here you can, maybe I should yeah, I didn't choose a very good, here maybe I can do these, and you can see that here all of these trajectories will be you can see that all of them they just damping in the y-axis, and by this choice of A you have this behavior. However, if I change this A to the bifurcation point, then you see that everything is changing here, right? So you have this difference, you have this changing in the stability. And for A, which is positive, then you see that those interesting things, that actually two families of like this is the saddle node, right? Like the creation of these fixed points, and by changing the parameter which is governing your equation, your differential equation. So with this changing in parameters, you have different behaviors, and the way that you can actually find these null lines and the fixed points and stuff, all of them are coming, you can see here, all of them is coming from these calculations, which all depends on those eigenvalues and eigenvectors. Therefore, if you need it, for instance, in your final project, you can calculate these things and draw the vector fields as well, and you see that, for instance, here the vector field is bigger than here, therefore here is faster than here, and so on. No question yet. Okay, so this was about this creation and destruction of the fixed points, right? So at the end, the conclusion here will be like this, that some fixed points has been created here, and or you can also say about the closed orbits or limit cycles, right? Both. And the way that for actually for splitting all of these phase portrait and talking about the regions, you need the null lines. Therefore, you should calculate and compute the null lines and understand the behavior based on the parameter. So if I just add this x here, like here, then I will have the transcritical bifurcation, right? So -5, 5, 5, and 5. Okay, So again, you can see those the changing in the stability. How? By, so if I have these kinds of trajectories, and if I change this A to 0, so you have these 3 parts, right? You have these 6 parts, 6 regions. If I have there is no null climb. There is one null climb. I see that now. Okay. So you can see that here it is changing, right? So you have to again compute these lines, and you can see that in this region all of them are repelling, and here you can see that all of them are absorbing to this part. Therefore you can say that there is something is changing here. This is the bifurcation point, because if I change it to +1, then about, it is same, isn't it? Like this, -1. So this is, we can see that here, for instance, all of them are attracting to this and repelling from this one, right? So if I change it to -1, I don't get that. Anybody has an idea? Yeah, it is. Yeah. This is -1 and this is 0, right? These null climbs. This is -1 and this is 0. And if this is in 1, and if I change it to 1, then it is 0 and 1. Yeah, this is the difference. So this is the point actually, that this null climb which is in 0 here, you can see that here it is repelling, right, from this null climb. But here, if I change it to -1, then this null climb which is in 0, it is attractive. It is an attractor. So the stability of these families of fixed points are changing because of the change in the parameter. So yeah, it was good to check. Okay, so in this transcritical bifurcation, the stability is changing, and in supercritical pitchfork, let me actually see if no. So in supercritical pitchfork, we have this positive cubic term, right? So now you see that here we have these null climbs and -1, 0, and 1. And it's important to know actually that this pitchfork is responsible for the explaining symmetries in the systems with symmetry. And here you can follow that actually all of them are so you have these two unstable fixed points, and if your system is inside these regions, if the state of your system is inside these regions, then it is absorbing to this, and if it is out of it, then it is repelling, right? And you can actually find that here you have one region, two regions, 3, 4, 5, 6, 7, 8, right? And the bifurcation point, you just have this. You just all of them, all of those two null clients has been vanished, and by after this bifurcation point, you can see that it is pretty much understandable. So it means that when your bifurcation parameter, which is a, when it is less than 0, then you have some regions like these two, like these 4 here, these 4 that if the state of your system, if it is in these 4 regions, then it is absorbing to this. However, if it is out of it, it is repelling, and it means something. It means if you talk about the membrane voltage, for instance, it has a meaning. If other types of things, this is the supercritical one, which we also draw the bifurcation diagram. And if I change it to minus x cubed, then for negative values of a, I have this structure, right? All of them are absorbing to this. But at the bifurcation point again, you can see the speed, like it is fastly coming and damping in the y-axis, and after that you have this change in the region. So here, for the positive values of a, you have these 8 regions, right? If I change it to positive one, like if I want to compare these things, it is like in the number of regions they are same, but in the stability of it is completely vice versa. So you can see it now right here. Like if I change it to -1, then still you have these 4 regions, but the state of your system will evolve completely differently. And this means that actually this is the subcritical one, right? This is the subcritical one, which is this one, which is minus x cubed. This is plus x cubed, and this is minus x cubed. It means that by changing, for instance, here in the supercritical one, if I have a positive value for a, then x dot is increasing, right? So for instance, a is equal to 1. Then if x is equal to 1, then this is 1 plus 1, which is 2. Then x dot has been, with the ratio of 2, changed and increased. However, here, if I have this a equal to 1, then this x is equal to 1, and this x3 is also equal to 1, and this means that sorry for this, that x dot does not change, because 1 minus 1 is equal to 1. And if this x is bigger than 1, like 2 for instance, then there's a very big damping in this x dot, right? However, here it is just increasing and increasing with the choice of a positive. And you can have the same argument, not the same, but similar argument for the negative values of a. So these kinds of differences, the way that you can interpret your equations in your which governing your systems, and their corresponding phase portrait, and the behaviors that you can see that is they are kind of new phenomena, right? The ways that you can actually interpret and connect these facts and the behaviors structurally and functionally are the ways that you can understand and write your report. So we talked about these transcritical, supercritical, subcritical, the pitchfork and saddle node of fixed points, right? So if we talk about, still we are talking about the fixed points, and now we want to talk about the Hopf bifurcation, which we do not have we do not have real lambdas. We have the complex lambdas now, and we have the Hopf bifurcation, which is very important in our work. So let me check if you have a question. No. Okay, so in Hopf bifurcation, when we have these imaginary values for lambda, like conjugates of complex conjugates of eigenvalues, then you see a kind of bifurcation which we call it Hopf bifurcation. It has this supercritical one as well as subcritical one. The basic idea is pretty much like this supercritical pitchfork and subcritical pitchfork. In supercritical pitchfork, the stability, again, the stability of your spiral, here we had a fixed point, but here we have a spiral. The stability of your spiral is changing and becomes to be unstable, and a limit cycle, a small limit cycle, will be created. So you can see that here, like we had a variable, a phase variable like theta, which this theta is actually our variable, like our angle, which is the representation of the periodic motion, which we use it for the oscillation. And you can also have another variable like r, which is the amplitude of u. You can, it's just the name, right? You can put it like theta dot and r, but this is just the standard form of it. So in this supercritical one, you can say that this ar minus r cubed, and here you have ax plus x cubed. This is the supercritical one. And wait, I think I did a mistake here. Yeah, it's just the sign, and the behavior is about the changing in the stability. So in the supercritical, it's important. It's important. Why it is important? This sign is very important, because this sign actually tells you that, for instance, here, if I have a change in r, then if r is increasing, then here this r will be increased, and minus r means that r dot will be decreased, and it means that it is always sending the state of the system to a smaller region of the phase portrait. However, in this subcritical one, you can see that this is a positive sign, and this positive sign means that if r is increasing, then r dot is also increasing, and therefore it is sending it out of like in a bigger region of your face portrait. So this sign is important. So, but however, about the name like supercritical and subcritical, it's about its bifurcation diagram. When you draw the bifurcation diagram, when it is in a very smaller one, then you call it like supercritical, and when it is in a bigger one, you call it in subcritical one. So the supercritical one here is like this. So with these choices of parameter a for positive values and negative values, here for instance for a negative, you have just a stable fixed point, and by changing this to positive values after this bifurcation, which we call it Hopf bifurcation, these spirals, which is like this stable focused, actually the technical term for that, is becoming to be unstable focus, and a limit cycle has been generated here, and you can see that the flows out of this limit cycle will absorb to this limit cycle, and the flows inside this is also coming like a spiral out, keep going, right? But not keep going here. It's absorbing and attracting to this limit cycle, and this is the moment like a equal to 0 here. By changing this parameter, you will see this Hopf bifurcation. So this is the normal form of it. However, in subcritical one, the cubic term has a different sign, which is positive. So by increasing this r, then r dot will also be increased. Therefore, it is destabilizing it. And the face portrait of it is something like this, that for negative values of a, you see that you have a stable limit cycle, and you have an unstable limit cycle inside that stable limit cycle, and you have a stable focus inside that unstable limit cycle. So because it is unstable, then it is repelling, and this spiral will toward and going to be focused here, and the other one is repelling and absorbing to this, attracting to this stable limit cycle, and out of it is also it's very obvious, right? So out of it is just attracting to that. However, by changing this r, so this is, if I change this r to this a, this parameter, which is my bifurcation parameter, to positive values of a, then you see that by increasing the r, both this term and this term, both of them is increasing, right? So r dot will also increase. So just forget about this minus r5 here. Just take these two terms here, and you see that both of them will be increased, right? Therefore, by changing this a to positive values, then your spiral will this unstable limit cycle actually becomes to be like kind of vanishes. It's vanishes with this like they are colliding each other. This unstable there's a kind of annihilation here. This unstable limit cycle and this stable fixed point, they are colliding each other, and the stability will change and the spiral will behave differently. But the outer one, which is stable limit cycle, will stay. Why we have these stable limit cycles here and here? Because of this term because of this minus R5. If we do not have this one, then we do not have this stable limit cycle out of it. But if we have it, the rest is the same. But if we have it, then we have this stable limit cycle like the bigger one. Therefore, always your system will be surrounded by this, and this is there are a lot of applications of these kinds of bifurcation normal form, like minus also another term like R5, which plays a big role in neuroscience as well. But if you just forget about it, still it is subcritical, and you just do not have these stable limit cycles, the bigger one. The rest is the same. Okay, so it is finished, and let me see here. Okay, so let me actually draw this here as well and see. Okay, so I have this I just put it like x, right? Ax minus r cubed. So ax minus x cubed. However, the y part will not be that much boring, and I just choose this one, like br squared, like b times r squared. So I can take it like 1, whatever. What happened here? Ah, right. Okay. Okay. So let's play with this, and as you can see that we just have this, and I do not see any kind of a spiral here. I don't know about you. Ah, this is because of that omega term. Yeah, I am doing it wrong. Because of this omega term, this omega actually brings you that this omega brings you, what is the name of it, this rotation, right? So I try like w plus this, like take it as 10 for instance, or 100 for instance. Nothing is changing, nothing is changing, nothing still is changing. If I want to see the other one, still probably nothing will changing. Okay, I don't know about it. I should think about it. Okay, so yeah, I should think about it. Wait, maybe these are. Okay, yeah. Well, anyway, I should think about it. So yeah. Any question? Isn't the function referring to a different representation? Yes, exactly, exactly. Theta is the angle and r is the radius, which you can say that actually theta is the phase and r is the amplitude. Uh, yeah. Aha, in the 2D plane, yes, it should be. You know, I think probably you think that we have x and y, and basically mathematically we say that, for instance, the radius like r, if we want to draw that, we say that r squared equals to x squared plus y squared, right? This is the equation for a circle. Like the ray with radius r, we have in the coordination we have x and y, and x2 plus y2 is equal to r2 is our radius. By However, here, yes, we can have we actually saw this like in this linear form. We saw this in the previous lectures. Uh, we just change our viewpoint. It's You are right. It's interesting, and you are right that actually, uh, instead of increasing our dimensions, for instance, from 2 dimension to 3 dimensions, like having x and y and theta, geometrically we design and we introduce something like radius, which is like, it is not, if the system is like, if the amplitude is the same, then the radius is constant. But if we have an oscillation, and in that oscillation we have the changes in the amplitude, then r is changing. So it is in this 2D plane, it should be displayed. Yes, I don't know why you arguing exactly why it should not be, because I am changing. Uh, yes, you are right. Yeah, 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 yeah. You are right, because my p plane here. Yes, I should rewrite them actually. Yes, I should rewrite them in a way to change this y and x to something, because yes, you are right. I am actually drawing, like, basically I am drawing theta here with respect to r, right? However, yeah, this, yes, you are right. I should rewrite them, and if you rewrite them, you can find them. Yeah, I think so. Yeah, yeah, you are writing something. Yeah, 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 yeah. Uh, yeah, I will. It's not something big, it's not a big deal, but I should rewrite them, and I want to talk about these topics a bit, like, because maybe some other people also watch this video, so maybe it's important for them as well. So in this Google sheet that you actually you wrote your names, you have three. You are able to actually work on that with three groups, right? But it is important, for instance, here like on this one we have three groups that are working on this. So basically, uh, we have to kind of sorting it, right? And so we have to we should have a kind of priorities. So I changed the I had to actually do these priorities based on the ones that said firstly. So first I got an email, and I can show these emails as well. First I got an email of this group, and then I got another email of this group, and then this group, they themselves came and wrote their names. So if we want to split the chapters of these books, therefore uh, they should these groups can there are two scenarios here. One scenario is that these groups work together and bring like a summary, like discussing and negotiating between them that which kinds of chapters they are interested in and stuff. Or if both groups, for instance, or three of them are interested in just the same chapter, then we have to. This is out of our choices, right? So then we have to actually choose between them and give some priorities to some other one. And I the only idea that comes to my mind is based on the time that they emailed me. However, maybe also we can do the random, like flipping a coin and change between them. So uh, if you are interested in the same chapter, then first you can negotiate. Otherwise, we can I don't know, we can do it based on chance, and the rest, or if we have to, if always that chance are like equally uniformly distributed, then we have to actually do these priorities based on the time that they emailed me, right? I don't have any other option. And same as this group as well, right? So and this I mean, I mean you the basic idea of all of this course and this way of evaluation is bringing a new phase to our evaluation process and having cooperation, right? This is why you are working in groups of 2, 3, and 4, right? So if even, for instance, we have if we have, for instance, here, sorry, one of them was education. For instance, here, if other groups also are here, then these groups can work together and split. Yeah.
Are you actually showing us which groups you mean? Because your screen is not shared anymore, so we cannot see about which groups.
I didn't see that. Sorry for that. Okay, so you have it now, right?
Yes.
Okay, sorry for that. I was mentioning about these three groups which are interested in summary and discussion of the chapters of this book, and the way that they wrote their names. Maybe they are interested in the same chapter. So first, it's better to use the negotiation and the rest that I said, right? So as well as these kinds of groups. So, or if other groups, like for instance this group, they are for instance interested in this educational attitude of the final project. If other groups also join this, then they have to negotiate, like splitting the subjects of the course between each other, or uh, we have to decide. And we do not have any, like, we do not have any discrimination at all here, right? But if we have to choose somehow, then we should use like a kind of chance or the time that they actually put their names, right? Otherwise, we do not have any other option. And so and we have a lot of works here, right? For instance, I don't know. Some of them are really interesting and even for instance easier. Some of them are even easier to do. Therefore, we have to be more concrete about it. But but all of them are interesting and opening a new door to a different field. And the course itself is also important because we want a kind of something to be sustained, right? A very sustainable improvement we want. Therefore, if some groups, for instance, join and making a toolbox here with Python programming and doing the same things like the way that we can find the fixed points, find the limit cycles, draw them, find the null clients, draw the vector fields, drawing the bifurcation diagram, the same thing. But it is a sustainable thing, and this is very valuable, and we can actually extend our cooperation to next generations as well, next participants, like next semester, or I said next generation, I didn't mean that. So yeah, so this was the thing. If you have any question here, and it's just important to the ones that are doing the programming, because we have to check their programs, they should also submit their codes. And please, your codes should have comments, and it should be easily readable. Otherwise, you see that you are 114 participants, and it's really not an easy job. So please help us for these evaluations. And also about the formats. So we prefer like having an introduction and then going like pretty much close to a very standard report, scientific report that maybe even can lead to a publication afterward later by working on that. But for the for this course and for passing this course, and I hope all of you get the total point. It's important to have some standard criterions here, right? Like having an introduction, your method, the figures that you plot, and their explanations, and the references, and if it is, for instance, if I'm sure that you also prefer, but we actually expect to for you to actually submit in LaTeX format, right? Writing in LaTeX format as well as the PDF format, and these kinds of things. So all of them are important. Like in general, I think this is an advanced course, and we are going to work together for a very sustainable improvement. Yeah, so I just ask for your help, and that's it. And if you have a question, please ask. So sorry if I am pronouncing your name wrongly, Annika Klassen. You you got your point, and because in this group, for instance, it was you, right? This one. So I mean, okay, okay, okay. So I also okay. So I also try to help you to find the materials as well, like the ones that you cannot find. But so we prefer to find them like in a very normal way. But and I am sure that you can all find them. But if you had some problems in finding the materials and stuff, for instance, this book, I myself still I couldn't find it. This book, and but we can obtain it. It's there is no uh, problem here. So about these materials as well, and like I just ask for a neat and clean and standard report, and informative, not like try to avoid like overdoing things, different in different ways, just saying the same thing. It should be informative, and it should be explainable enough, but avoid overdoing and over talking about something that I am not also very good at it, but I know that yeah, it makes sense maybe. Okay, so if you have a question, I am here. Otherwise, wish you a great weekend ahead. Okay. Ah, you're welcome. Thank you also, and have a great day. Bye.